Okay, in this video we're going to look at the use of integration in the determination of present value. We're going to start with a discrete time example, and the application is to the bond formula that we use in finance. Assume that a bond gives a return every year and that the discount rate is R. What is the present value of an infinite stream of K, where K is the return in each and every year? So we write the value of a series over n years, where in each year, at the end of each year, we get K. So we discount the first K by this amount. Here we discount it by 1 plus R. The second year, K is discounted by this term squared. In the third year, it's discounted by an R cubed, 1 plus R cubed, and so on, till we get to the final term here. And we have this, we call this a geometric progression. What we do next is we multiply Vn by 1 over 1 plus R, and we multiply both sides. So then this circled value here becomes a square. This one, the second term, becomes a cube, and so on till we get to the last term, which we multiply by 1 over 1 plus R, which in turn gives us that term there. Now we're going to subtract the second equation from the first, and what we get is this on the left-hand side, but on the right-hand side we're left with this term here, and we're left with this final term there. Everything else cancels. So these cancel, the thirds cancel, this one cancels there, and we're left with just those two terms. So now what we do is we rewrite the left-hand side by bringing 1 plus R over to here and dividing by 1 plus R, subtracting 1, so that leaves R at the top and 1 plus R at the bottom. And we do the same thing, we factor out this K plus 1 plus R over here, and we're left with this. Then what we end up with is this expression here. We take the limit as n approaches infinity, which gives us then K over R, 1 minus the limit as n approaches infinity of this last term, 1 over R, multiplied by, this R should be gone, over 1 plus R to the n, and that gives us K over R. The current value of a bond that pays K dollars annually in perpetuity is then given by this value V. And it's very easy to calculate this bond formula, which we rewrite as K over R, or as the annuity equals RV. So let's say that V is $100, okay, then if the interest rate is 10%, we get K is $10. If the interest rate is 5%, K is $5. But if you've bought the bond for $100 and you're getting an interest rate of 10%, so K remains $10, then when R goes down, we have that the value of the bond goes up, because K over 0.1 is equal to 100, K over 0.05 is $200. Remember that K equals $10 per year. So that's what happens, okay? And it's a very useful formula to remember, because if the interest rate goes down, the value of the bond goes up. If the interest rate goes up, the value of the bond goes down. Now, suppose we have an initial investment, V0, that grows at an annual compound rate, R, for n years. Then its future value is given by this. This becomes V0 instead of K. And we can alternatively write that as V0 being Vn, which is the future value, divided by 1 plus R to the power n, where n is the number of years that we invest that initial value for, that initial investment. So we can write that as 1 plus R to the minus n Vn. Now suppose that compounding occurs every 3 months, so 4 times a year. What we do is we divide the interest rate R by the number of periods. In this case, 4. So if we had an 8% interest rate divided by 4, it would be 2% per quarter. And we multiply, or the superscript here is m times n. So if it's 10 years, 4 periods, then we've got 40 periods total. And you can calculate on your own what happens if you take R and divide it by m and take this ratio as 40 as opposed to just 1 plus R to the 10 years. You can see the difference that compounding every 3 months makes. Now this can also be written as, the current value of the investment, given that we have this future value v of n, and we discount. In this case, we have that minus sign here. In the limiting case, interest can be compounded continuously so that the distance between points in time at which interest is calculated, that delta t, approaches zero. And that's what we're going to do here. So now we have an initial investment v0, and we want to know what the future value is going to be. And we look at the limit as m approaches infinity. So the number of delta t's that we have becomes infinite. So we break that year up into an infinite number of time periods. Then we take the natural logs on both sides of the expression. And what we do first is we allow z, or we define z to be 1 plus r over m to the rn. So this expression here, including that n, becomes z, so that we can write this equation here as this one here. So the limit as m goes to infinity of z times the initial investment. Now we take the natural logarithms on both sides of the expression for z, and that gives us these results. Since the log of 1, so we got a 1 in here, equals 0, both hm, so we have r of m, h of m goes to 0, and g of m goes to 0 as m approaches infinity. So think about it. Here you've got, this is your g of m is going to infinity, so this is 1 over infinity is effectively 0. And the same thing here, that log of 1 is 0, r over m is left as m goes to infinity, that goes to 0 as well. So how do we save this? Well, we use L'Hopital's rule, and what it says is that the limit as m approaches infinity of h of m over g of m is equal to the limit as m approaches infinity of the derivatives of h of m, so the derivative of h with respect to m divided by the derivative of g with respect to m. That gives us exactly the same result. So what we're going to do is we're first going to take the derivatives. The derivative of hm with respect to m is given by this expression here. And for g prime m, it's given by this expression. And if you look, you basically, the minuses cancel. So when you divide h prime m by g prime m, you'll see that the m square cancels, the minuses cancel, and what we're left with is an expression r of n divided by this here. And what we do is we find the limit, and it turns out that it's r of n plus the limit of r of n divided by m, which is 0, and we're left just with r of n, r times n. Upon taking anti-logarithm then, so we take the anti-logarithm of the original z, this, remember this was equal to z, and we take that and we get this expression e to the power rn. Note from the previous page, from here, that if r is 1 and n is 1, then we get e on the right-hand side, and this expression is left here, except now the r is 1 here, this r, and this n is 1, so we're just left with that m and this 1 over m. So in that case, we get v0, which is our current value or initial investment, is equal to e to the minus rn times the or future value, or we can calculate the future value by multiplying the initial investment by e to the r times the number of years in our horizon. Present value of a stream of annual payments then, and we'll denote those for the time being as a function of t, over a long period of time given by capital T, is then given by this expression. Notice here we've got the integral. So the initial investment, or the current value of the investments, is equal to the integral from t equals 0 to big T of e to the minus rt a as a function of t times dt. Now, assume that a of t equals k, so in every period we're earning k, and then we can factor out the a of t, and we have k on the left-hand side, outside rather, the integral, and we get the integral from t equals 0 to capital T, e to the minus rt dt. Upon straightforward integration, we get this result here. If we integrate this, and now we let this t go to infinity, and you see when t goes to infinity, this expression here goes to 0. So we're left with k over r. So the current value is given by k over r, which was the exact result we'd found for the discrete. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.